Okay, this is a video I'm making to demonstrate how to export experimental measurement data from Polytec PSVSoft and import that into Siemens Simcenter Testlab for post-processing through the modal analysis application therein, and ultimately exporting to universal file format .unv. This is a piece of work that we've been immersed with at UTS in the vibration lab at our UTS Tech Lab facility on our Botany campus for some time. The video is primarily aimed at junior researchers and learners working within the laboratory, but should also be of interest to others, and including hopefully Polytec manufacturer, software vendors like Siemens Simcenter as well, solution manufacturers, and other collaborators, other research collaborators. I am sharing one screen here where we've got a draft paper that's been prepared by one of my former capstone students, as well as some other researchers, visiting scholars, and so on. We are focused on axisymmetric structures. In this case, these rings, rectangular cross-section rings. I'm remotely connected to two other systems. This system is the data management system that runs our Polytec PSVSoft solution with our PSV 500 extra scanning laser Doppler vibrometer. That's in the laboratory at the Botany campus. And this machine that I'm connected to here is in my office on our Broadway campus. And each of these two systems is able to run different pieces of software, and I'm going to work through a process of transferring files and data from one to another, hopefully via Teams, essentially as the location where we'll share the data. The PSVSoft system, the DMS data management system, is running Windows 10, I think, and it's the system that was delivered with the PSV system, and hasn't been upgraded. Windows isn't generally connected to the internet. Every time we do so, it tries to do a Windows update, but we don't update the operating system on that PC. The system that I'm running at Broadway is a Windows 11 system, and I'm giving this information because I know that the software manufacturers often like to know what system we're running when we have things that we're showing and demonstrating in software. So here is the system that I'm operating, primarily Siemens Simcenter Testlab on the remote desktop. So looking at the Polytec system, here are a series of measurements that have been completed previously of these axisymmetric structures, these rectangular cross-section rings. I'm looking at this one in plan view. The data has already been processed. We've got various mode shapes, experimental mode shapes have been identified, are shown by these various peaks that have identified those shapes. There are some things to take note of in that when we set up the measurement campaign, we have done a 2D alignment, and the process of doing a 2D alignment is to align the laser vibrometer scanning system with the image that's coming from the camera system. And a range finder is used in the process of doing that. It essentially identifies the standoff distance of the target plane from the vibrometer head, and then the X and Y positions of various points that are subsequently defined on the structure to make a measurement grid should be close to being, if not in agreement with the actual physical dimensions of the disk. Now, we've done some experimentation with this, and we have noticed perhaps that this isn't yet quite perfect. So that's something to check in the future, and I will be doing another measurement campaign where we will use the Polytec reference object that we've purchased previously to help make sure that when we do this 2D alignment, we do get sensible dimensions for these rings. You can see in the paper here that the ring dimensions are given. It's 107 millimeters to the for the radius, with a thickness of 30 millimeters. So 2 times 107 plus 30 is 244. And if we look at the information coming from these adjacent points on this image, you can see that these values are different to that. So if I look at this position here, so it's primarily going to change in X, because X is horizontally orientated, and that's minus 142, let's say, millimeters. Of course, it's not to the absolute extreme of the disk, but this one is 129, so 129, it's more like 270 millimeters, which is clearly very different to our 244 millimeters that we expect across absolutely the extremes of the ring, whereas obviously with this grid we're inside of the extremes of the ring, because we need to ensure the laser beam is on the disk, so we don't go right to the edge with our measurement grid. So we have a problem there that we need to resolve. Another issue that we didn't think about at the time that we were making these measurements is that we need to have a location, a measurement point, directly beneath the excitation location to be able to do a modal analysis like properly, as you would in, for example, Siemens Simcenter Testlab. You would identify the degree of freedom where the electrodynamic shaker is attached to the structure. If I turn off these clipping planes, then I can zoom out a little bit here, and these are the cables to our electrodynamic shaker. Now, this is obviously, I can't see behind the ring, but the electrodynamic shaker Q source is QW, lightweight shaker LWS, QLWS is attached to the back of the ring. Now we need to know, or we need a point that is directly behind the location of the shaker, the driving point. And I don't really know where that is, but I think it's somewhere close to point 133. If I go back to having the clipping planes fully on and view this from the top view, zoom back in again, then you can't obviously see the shaker. It's connected to the back side of the ring, and therefore we have unobtruded access to the top surface with the scanning vibrometer. Unimpeded, I should say. It's sitting on a foam piece of foam with a corner cut out here that allows us to position the shaker. And maybe it's actually, perhaps it's even maybe nearer here at 0.18. We need to work that out. What we need to do is connect the shaker, and then when we build the measurement grid, we need a point on the top of the disk that we can say, right, that's where the shaker is, and we draw a single point manually, and then we can build a grid in addition to that, and then we will have a point at the reference location, the driving point. Why am I telling you all of this? Because subsequently we're going to export these data to an ASAM ODS, which is an interchangeable file format that allows us to swap data between different modal analysis packages. So the process of doing that is as follows, and I'm just trying to remind myself which folder I've been saving these data in. Actually, we're going to use the Polytec folder here. So these are measurements that were collected by Ella previously. So I've had 3 previous attempts at exporting the ASAM ODS data, because we've been iterating on this prior to creating this video. This is a different project to the ones that we've previously exported, so I'm doing this from fresh today. When I hit save here, I'll be able to choose some options as to what I would like to export. Now, we've basically been exporting everything that's possible to be exported. We actually don't need necessarily everything. We definitely need transfer functions, frequency response functions, I should say. So we should probably, or we could just, take everything that's in Vibe and Ref, but the file size is not enormous if we take everything. Now here's where I get to define the location of the shaker. You could see previously that was at 138 because that has been carried over from a different project I had open earlier. I'm now going to swap that value to 18, and this will come up subsequently when we see the data being imported into Simcenter. I'm also exporting the geometry. The geometry is quite important to have out of the ODS, but there are some challenges with that when we import the geometry into Simcenter, and that's primarily the purpose of this video, as well as some other aspects. So I'm going to work through how we properly resolve the geometry that we import into Simcenter Testlab. So this now should export all of the data essentially from this project into that location. And if I go to the Teams channel and open Windows Explorer, so I'm in the folder there that I identified. I'm using this folder here that Ella created that all capstone project students can access. So here are the ASAM ODS exports, and the one that we just exported are these two here. So there are a pair of files, an ATFX and a BTF. Simcenter just recognizes this as one file, but those clearly have just been created a moments ago. So I'll put those in that location there. I can then come across to the other system. Probably take a while to upload those new data. And there they are a few seconds ago. So I'll download those on the other machine. And they'll just go into the downloads folder, I think, which is here. Okay, it's still downloading. Whoops. Where is the downloads folder? Let's try again. Yeah, okay, so those are there, compressed currently, but I'm going to move those into, I'm not doing it like that. Let's go back, copy those, put those in this Testlab data folder for now, paste those there. So then if I come into Testlab, I can actually start a new project. I think that's the right approach. I hope this video won't turn out to be too long. I'm going to work through the process as comprehensively as possible so that people can replicate it subsequently. So here's the Simcenter folder that I just put those measurements in. And these are the ones here. So we can navigate in there, we can have a look at those. We can also right click on that and convert to Testlab. And then doing that, we should identify where we would like those data to go. So I'm going to put those in the same location. Now this takes a while. You can see it's converting here. Because of course there are a lot of functions in that test series folder. That's all of our FRFs, auto powers, power spectral densities, energy spectral density functions, coherence functions, and some time data. We will get a warning message in a moment telling us that it can't import time data into the project, because time data in Testlab, or throughput data as it's called, is typically is always stored in a folder outside of the project. So that's that warning there. I don't know that we've necessarily saved all of the time data when we did the Polytec measurements. Perhaps we just saved some blocks that are used to create the averages rather than like recording the entire chunk of time data. So that I'm not entirely sure about that warning. At that point, I shall close this project, which is basically just a blank project that I used to be able to access the folder. Whoops, cancel that. And then open the imported project, which is this one here, 1022. So just opening now this converted Testlab folder project, which has come from an ASAM ODS file. So this is looking promising. If we go into the navigator window, it's taking a while, I think, perhaps to open the project rather than to move to the navigator. Sure why that's okay. There we go. So here we're in this project. Here are these data, this test series data, and here are all the various different functions that exist within here. So if I go to this folder, in fact, I could go to either of these folders. I can list all the blocks that exist within this folder. And now I've got a series of links here to these various functions. I'm filtering on the FRF at the moment because that's the function that's of most interest to us in modal analysis, but I can show all of those functions, as I mentioned before, so power, coherence, functions, cross powers. These are all created when we do a measurement campaign. I've also got data that are included here from the processing of the results that was done in the Polytec PSVSoft, because those results that we've actually also done the modal analysis in PSVSoft. So if I have a look at those, these functions now are for each of the frequency bands that were selected. There are some measurements here. There are some processed results here. So these are, if I go to this particular window and turn it onto preview mode. So for each of the 154 points in that spectrum, there is a set of values here for the measurement of the force and for the velocity that was measured by so that's a PSD, there's a millimeter per second squared, millimeter squared. Now there's obviously a velocity function there, so various different processed parameters for the measurement made by the laser vibrometer, and at the same time the measurement of the reference force transducer integrated within the force transducer. Integrated within the lightweight shaker. So that all looks reasonably promising. We can see these functions. If I use a Bode plot instead here, filter on the FRFs. Let's put a Bode plot in here, which is amplitude and phase. Let's make that preview mode. We can scan through those. And make that. And we can look through those one by one. So they're very nice looking frequency response functions with amplitude and phase, as we would expect for a very well behaved, lightly damped structure such as these steel rectangular cross sections rings that we've made measurements from. Other parameters of interest, the coherence functions, or functions of interest, I should say, we typically review those actually just on an XY, on a front back display, because there's no phase. Turn on preview mode and we can scroll through those coherence functions. We want to have functions with good coherence, except we might find the odd poor coherence at the anti-resonances, which is what we observe here. Some coherence functions are a little bit fairy, but overall these are very nice looking coherent functions with values of 1 everywhere that we have a resonance. And the other thing to note from all of these data are that the reference DOF ID has been identified correctly as 18. That was the step that I made when I exported, or when I specified where the reference was in PSVSoft. So when I create the FRF, when I exported the ASAM ODS, I should say. And the challenge comes when we start to try to do something with the geometry that we also need. So if I open a geometry display here, try and have a look at the geometry, but actually there's nothing inside. Normally there would be a component or multiple components identified here, and nothing comes up. If I add in the geometry tool, which I can do by adding this in here, then I can see that there is some geometry, but what we're missing that we need in Simcenter Testlab when we build a project from scratch, or when we do a modal analysis, a modal acquisition campaign within Simcenter, we identify a component. Then we, for each of the components, have a list of node names and XY data. So that information comes through the node names and XY data, but we don't get a component name. So we have to use a workaround to resolve this. And I'm going to actually copy those data into an Excel spreadsheet. So those are those values, and it doesn't recognize them as numbers. So I'm going to convert those to numbers. There's something going on there. And also the surfaces, which we can see here. If I turn on the model, for example, we can see that the names are there. But in Simcenter Testlab, we need to have component : name for the FRFs to be associated with it. I'll demonstrate that in a moment. But to begin with, I'm just going to copy these surfaces out into this Excel spreadsheet. Same problem, not recognized as numbers. Okay, so those are there. Now, if we were to just carry on with these data, so you can see that it identifies these FRFs, it finds the 154 FRFs, but it's got this component : 1, component : 2, etc. And these FRFs are not shown on the geometry here. So what I should see when I go through these FRFs here in modal data selection is that as I change from one FRF to the next, the component that the FRF corresponds to is identified in the display. And that's going to give us a problem, because when we process these data, it won't know what to animate them. It won't be able to animate the results on this geometry. So we've got to fix that. So I'm going to go back in here and delete this geometry and save the project. I'm going to, just for the, I think it's better to close and reopen it, because I did have some problems before when deleting geometry from a project. It didn't like it, wasn't too happy with it. So I will reopen this. Now I will, because my FRFs are labeled root, that's going to be the name of the component, which was missing previously. Okay. So just to verify, is here my velocity? No, they're my bands. That's my band data. There's vibration reference. Root : 1, 2, 3, 4, 5, etc. So we'll call that root, and we go to nodes, get these data back, paste. Now, what I did notice before was that maybe it was just the surfaces. So if we paste those there, then we get 1 to 155 and all of the corresponding X, Y, and Z data. So if we accept the table, then we get our geometry here. And if we turn on the names, you can see there root : 150, root : 110, etc. You can actually remove the prefix of the component from that if it looks a bit untidy, which it can do, but it is needed for us, and I'll show that subsequently. Let's just put that back on. I don't have any lines. I could go around and join all of these data points together with lines, clicking one by one, or I could do that by pasting into these tables if I had that information. I don't have that information. What we do have is the surfaces. So I will go back to that surfaces tab from Excel, copy that. Now, I did notice before, initially when I create surface from scratch, there were only 50 lines. So I have to paste this, and then it stops at 50. Right, so then we accept the table. It then, what happened? Paste those, accept. No, that's not working as it did before. Why is it removing those? It should create triangles that connect 1 to 2 to 3 nodes, but there's a problem with that. I'll just save this and I'll reopen it, see if it will work properly this time. This did work previously. Go back to the surfaces, copy those values. Now it doesn't show me the table here to paste into, which is that's no good. So the only way I can rebuild the surfaces is to connect 3 points together like this, double click on the last one, and that's a surface. So I don't know what's exactly happening there. We'll have to live without the surfaces for the sake of completing this video, otherwise I could spend a lot of time trying to debug what's happening. At least now we've got some geometry that will be associated with these FRFs. Unfortunately, unless you turn on the markers here, because the surfaces are missing, we don't get to see anything. And those are those points and the names, if I want to include the names. But as I've said before, it gets a bit messy. But now let's show the points on the geometry. So there, immediately now you can see that as I move through these FRFs, the point is being identified on the frequency response function. If I select the whole column, then you can see that all of the FRFs are present for the entire geometry, which was the thing that was missing before. So now we're looking pretty good to be able to do a modal analysis and animate the results on the geometry that we've imported and built. So if I select a band like this, I'm viewing all of the FRFs. I can also have a look at the sum FRF. I can turn on the mode indicator function in this kind of a solution. So wherever I get a drop in the mode indicator function, this is a single reference mode indicator function, then I expect to find a resonant frequency. Of course, this is an axisymmetric structure, so there are split doublets, pairs of modes that are diametrically rotated with respect to one another at each of these actual frequencies. We don't have the resolution to see those. We don't have multiple references. If we did, we might be able to pick up the 2 orthogonal modes at each of these resonances, but we don't have that in this case. If I look at the stabilization diagram, perhaps I need to turn the mode indicator function off for this, just so that I can see the potential poles. You can see we get some very nice stable poles here. This is a very nicely behaved structure, lightly damped. So I can go through here and choose these stable poles quite straightforwardly with a relatively low rank. This is an example here where there may be 2 split doublets here. We've got vectors alongside stable poles. As we increase in rank, perhaps there are 2 frequencies here that are quite close. It's an asymmetric. Of course, it's axisymmetric, but really it's been made, so it's got some asymmetries. The larger the asymmetries, the wider the frequencies are between these 2 split doublets that occur at these various frequencies. Not all of these mode shapes will be a split doublet. Some of them are m equals 0 modes, and therefore there's only one m equals 0. It's for m equals 1 and above nodal diameters, and above that you get split doublets. So I see 8 peaks in there. I select eight poles, and then I can move through to the shapes sub-tab and calculate these data. And of course, because there's no surfaces presently, I need to turn on some node markers, get rid of the names. If I had lines, I would also see lines. And it doesn't know how to fit the model when there's nothing in the display. That's what I'm doing there. So let's have a look at mode number 1. And there you can see we get a very nice looking mode shape as we expect. I don't know if I'll get any colouring because I've got no. Oh yeah, no, I get colouring on the DOFs, of course, and then I can move through these shapes one at a time. So that's the torsional mode, m equals 0. Now these are all modes that exist for this rectangular structure with vibration that's primarily in the z-axis, so on the optical axis of the laser vibrometer, because of course the vibrometer is sensitive in the optical axis direction, and also we're exciting the structure in the z direction, which is coincident with the vibrometer optical axis. This video is now very long. I understand that. That's the m equals 1 torsional mode. That's an axial mode. I think m equals 4. And m equals 2 torsional mode, and so on. So some very nice looking mode shapes, exactly as we expect to see from our analysis in PSVSoft, but with those data processed using Siemens Simcenter Testlab, a gold standard modal analysis package. So 944.5 Hertz, that's the m equals 3 axial mode, which is this frequency here, 944.4 Hertz. So that looks good, but we get damping ratio here as well, and we get upper and lower residuals. We get much more control using this tool than we would otherwise get. We can also look at doing modal synthesis. We can explore the mathematical curves that we fitted to our experimental data, which are the green curves, the mathematical functions, and the red data is the red curve is the experimental data. Here you can see quite nicely this possible split doublet situation here. We saw that in the stability diagram. We saw there are definitely two close modes here. There might not be a split doublet. It could be that this is a mode that's got out of plane motion, for example, what we call a radial mode, but we're not exciting in that direction, nor are we measuring in that direction, so we only see a small peak. It may be that because of the nature of the geometry, it's quite close in natural frequency to the the axial mode that's at a similar frequency. These are the sorts of things that we would be able to explore using finite element analysis, and that's what this paper looks at. This paper predicts using finite element analysis where these frequencies should be for these various rings, and then looks at experimentally determining them and comparing and contrasting experiment with simulation. And there are some tables in the back which give the full description. So perhaps for this particular ring, there are some close modes, axial and radial in extensional, and that's maybe what we see there, but this requires much more analysis. Then from these data, okay, let's save that project. Then we can go back here to export this to a universal file. We can export the entire project, which may or may not be useful, or we can just export the mode shape. I've been exporting the mode shape, just share these measurement data with a colleague who's working with me from PERMAS in Germany. So then if we export these data here, you can see some exports from previous projects. In this case, we had to turn on the normalized modes option and the right elements in the dataset number 2412. I've misnamed that. But that's the process for exporting to universal file format. And I thought I would be able to grab the file name from here, but I don't see that easily. So I will just rename this manually, because this is the 3rd of October measurement that we did, 30 10 kilohertz chirp Q sources. Okay, so I export that to universal file format, and that UNV file is now here. And that is the end of the video, I think. I've demonstrated what I'd hoped to demonstrate, with the exception of the surfaces importing or replicating of the surfaces not working as I expected. In the geometry tab, we've shown how to export data from Polytec PSVSoft as in ASAM ODS, import it into Simcenter, work around the fact that the geometry isn't rendering or isn't being properly presented, let's say, in Simcenter. So I found a workaround to rebuild the geometry manually. Then I've been through and done the processing in Modal Analysis. We've produced results using time MDOF, and we've had a look at the shapes. If we go back to the navigator, we can see the geometry now actually is possible to be imported into here. Again, turn on the node markers, fit the model, go to the processing, and we can drag those in here. And these measurements, or now these results, can be exported as GIFs, for example, or as active pictures with embedded data. We can right click on here, and I've shown this in other videos that I've produced previously, export to a video, for example, here as an MP4 or an AVI, some other format for reporting purposes. We would probably use colouring and various other things to embellish the animation to make it more easy for the end user to interpret what's happening. Thank you for listening. Hope that was helpful. Sorry it ended up being rather long, but it is hopefully very comprehensive. I've been Ben Holcomb. I'm Associate Professor at UTS in the School of Mechanical Engineering, lead of the Vibration Lab at our Botany campus, and that's me. Thank you.